VLSos here. This is a video lesson on using algebra to find limits. And it's going to focus on two main common useful techniques, but it's certainly not all of the ways that we can use algebra. Let's do a couple of example problems. This is the limit as x approaches 1 of 2x squared minus 2 all over x minus 1. This is a finite limit because the approach statement is going to a specific value, not infinity. The first thing to do when attempting a finite limit is to try to take the limit right away, substituting in the value into the expression and seeing if we can evaluate the expression. In this case, when we do that, we get 2 times 1 squared minus 2 all over 1 minus 1. And if we simplify these expressions, 1 squared is 1 times 2 is 2, minus 2 is 0, over 1 minus 1 is 0. If this were just something divided by 0, then we would have determined that the limit doesn't exist by this direct substitution method because we'd be dividing by 0. But because the numerator is also 0, we have kind of a special case. And I'm not going to say that this expression is equal to 0 over 0. I'm going to use the arrow because we haven't determined the limit yet. We're approaching 0 over 0. So remember, a limit has an approach statement, and in this process of the work, we're still considering it as approaching 0 over 0. But what do we have here? If we're thinking about trying to find the limit, now how do we think of this? This result could mean that the limit is 0 because the numerator is 0, so 0 of anything is going to be 0. But similar reasoning could say or suggest maybe the limit is 1 because something over itself or something divided by itself is always 1. So maybe the limit is 1. Maybe because we're dividing by 0, the limit is going to be undefined because we can't divide by 0. Or, for other reasoning, maybe it's something else. Because we have many different ways of trying to resolve or understand what approaching 0 over 0 means, it means that we cannot determine the limit. It doesn't mean that it's any one of these things yet. It means that we can't have more than one answer to the limit question. We can only have one of these, and we don't have a way of determining now which one it is. We would say that this is indeterminate. The limit has not been determined by this process of direct substitution. So we have to use another technique, and there is a technique called Newton's method that we're going to learn once we know more calculus. But in this case, we don't need that fancy calculus technique because we can simplify this expression with some algebra. And the algebra that we're going to use is going to take advantage of the difference of squares factoring pattern. A squared minus b squared, literally the difference between the squares of two things, can always be factored as a plus b times a minus b. How does that help us here? Well, this expression we are going to factor. We're still going to take the limit as x approaches 1. But we're going to manipulate the numerator. The first thing that we're going to do is we're going to factor out a 2 out of these two terms. So we have a factor of 2. And when we factor 2 out of 2x squared minus 2, what remains is the difference of squares, x squared, and we're going to think of 1 as 1 squared. So in the difference of squares with an x and a 1, we get the factored form x plus 1 times x minus 1. What I've done is I've factored the numerator in this expression. The denominator does not need to be factored. It is the factor x minus 1, which matches one of the factors in my numerator, and thus I can cancel them out. Very typically, when we're using algebra to manipulate the limit in order to simplify it, it often involves factoring of some sort. And here we've used difference of squares to factor and cancel. So we are taking the limit as x approaches 1 of 2x plus 1. And we're back to the strategy of determining or attempting to determine this limit by direct substitution of the finite value 1. So this is the step in which I'm going to try to take the limit, is 2 times 1 plus 1, and the algebra simplifies or evaluates quite simply. 1 plus 1 is 2 times 2 is 4. That's the limit. Notice that before, when we were wondering what the 0 over 0 limit form was going to be, it ended up being other, because it's 4. I'm going to do another example problem. This time we're going to take the limit as x approaches infinity of 2x squared minus 7 all over x squared plus 4x minus 1. So the limit is not a finite limit, it's an infinite limit. And the expression that we have is a little bit different. We don't see a difference of squares pattern here probably, but factoring is still going to be our general strategy. First of all, we could use the concept of dominance to determine what terms are going towards infinity at different rates, and the term that will go towards infinity fundamentally faster will dominate and thus determine the limit. However, dominance is a quick, informal, conceptual way of finding a limit that's quite useful. The strategy that I'm going to show here is algebra, so it's a more formal process, and then it would be the solution process that we would consider to be proving what the limit is. So how do I take this limit? I'm first going to factor the numerator and denominator, but I'm going to factor with an attitude that's a little bit different because I don't have a factoring pattern. I'm going to decide to factor out x squared from the numerator. Even though x squared is not in the term minus 7, I can still force it as a factor out of that term. And we'll see what happens when we do. X squared factored out of 2x squared leaves the 2. So what is left after we take x squared as a factor out of negative 7? It's going to be negative 7 over x squared. If we wanted to be convinced why this is negative 7 with an x squared factored out, I could check by redistributing. When I do, the x squared times 2 remakes that term 2x squared, and x squared times 7 over x squared would cancel out the x squareds, leaving the negative 7. So I know that I can check it and go back. That's why making this in the first place is the correct way to go. But what did it help? Well, I'm going to factor out an x squared from the denominator as well. X squared factored out of x squared leaves a 1. X squared factor out of 4x. I've already got an x there, so 1 cancels, and the other has to remain in the denominator or be represented in the denominator. So 4 over x is 4x with an x squared factored out. Finishing up, negative 1 is negative 1 over x squared once I factor out an x squared. I'm still taking the limit as x approaches infinity. I've factored. We could call it force factoring. Why did I do it? Because I can cancel out the x squareds that I factored out as a common factor and eliminate them, changing the expression to this one here. Why would I do that? Well, I'm going to put the work up here and continue. This expression here is the limit as x goes to infinity of what remains of these expressions. And the way I'm going to list the next step of work is going to look a little odd until we see how it benefits us. I'm going to list the 2 term as a 2. That doesn't change. But the 7 over x squared, I'm going to show as the product of 7 and 1 over x and 1 over x. I am listing out the factors of that term. And I will divide by 1 plus 4 over x seen as 1 times 1 over x minus 1 over x squared shown as 1 over x times 1 over x. Why would I do this? Because I'm taking advantage, or I'm reducing the problem or converting the problem into being able to use a limit law, the most helpful one, and that is defined by calculus to be the limit as x goes to infinity of 1 over x is 0. This is a limit law. It's a kernel of factual mathematical truth that I can now apply to this more complicated limit. I'm taking the limit as x goes to infinity, and I'm going to take the limit of each separate factor within all of these terms. When I do, I can show the work. I'm taking the limit now. The limit of the constant 2 still remains 2, minus the limit of 7 as x goes to infinity is still 7. But now the limit as x goes to infinity of 1 over x is 0 by definition. And I multiply by 0 again. All over, limit as x goes to infinity of 1 is 1. Limit as x goes to infinity of 4 is 4. Times this 1 over x goes to 0 again. And we subtract another 0 times 0. Look what happened when I broke up the expression into these factors, found each limit independently. I've got the expression now 2 minus 7 times 0 is 0, over 1 plus 4 times 0 is 0, minus 0 times 0 is 0, and this reduces quite simply to 2 over 1, or just 2. I've found the limit. In this case, the limit of 2 would be hard to see directly from the original expression. If I took this limit by thinking of the expression or these terms before breaking it apart, I would have gone in this direction. The limit of 2x squared as x goes to infinity is infinity minus 7 over x squared is infinity plus 4 times x is infinity minus 1. And we would get, by that direct use of limit laws, infinity over infinity. This doesn't help because, just as the previous problem, how do we think of this? Is this infinity because of the numerator? Is it 0 because of the denominator? Is it 1 because it's something over itself? Or is it something else? Well, it turns out it is something else. It's 2, because we went through this algebraic process that then only relied on this limit law in the end to justify thoroughly and formally.